Okay everyone, so today let's pit start with chapter 5.1 areas and distances. So first let's use the area of a rectangle to find the net area. So in this example, we will use rectangles to estimate the area under the curve of the parabola f of x equals x squared from 0 to 1 as pictured below. So we're using 4 rectangles of equal width, which is n in this case. So as you see, we have all of the points listed from which we'll use to estimate the area. So basically we're just finding the area of each of these individual rectangles and adding them together. And when we get that, we get about 0.469, which happens to be an overestimate. As you can see, there's a lot of area of the rectangles that's above the curve. Next, we'll use the area of a rectangle with left endpoints instead of, so in this example, we'll use left endpoints on rectangles to estimate the area under the curve of the parabola f of x equals x squared with 8 strips or subintervals from 0 to 1. Add up the sum of all the areas. So we're doing the same thing we did last time, only we're starting with the left endpoints. So when we do all of that and we add all of the areas together, we get an area of 0.273, which as you can see is an underestimate considering a lot of the area under the curve is not covered with this. So when we use the right endpoints of the same problem, we take the right side of the rectangle instead, and once we find the area of all those rectangles and add them together, we get an area of 0.398, which is, as you can see, an overestimate, considering that there's area of the rectangles that are not accounted for, or that are above the curve, that so there's like more area than we need. So what we're doing here is basically we're finding the net area under a curve. So the definition we'll use is the area A of the region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. So this can be showed in the notation A equals the limit and approaches affinity of the summation n equals, or 1 equals I, of f of x initial times delta x initial. So if delta x is the same, A equals the limit as n approaches affinity of f of x1 plus f of x2 and so on and so forth times delta x. This can also be shown as A initial equals f of x initial plus f of x initial plus 1 over 2 times delta x initial, which is area initial equals base 1 plus base 2 over 2 times height, or what we said before. So next we'll use the area of a trapezoid to find the net area under a curve. So we've done rectangles, now we're going to try using trapezoids, which is definitely a lot more accurate. So in this example, we'll suppose the odometer on a car is broken and we want to estimate the distance driven over a 30-second interval. We take the speedometer readings every 5 seconds and record them in the following table. So there's all the times and velocities. So we'll convert the velocities to feet per second because 1 mile per hour equals 1.47 feet per second approximately, so that we have unit agreement. So find the approximate distance over the first 5 seconds from 0 to 5 seconds. So when we do this, we'll add both the sides times. and divide that by 2. So 25 plus 31 divided by 2 feet per second times 5 seconds, which equals 28 feet per second times 5 seconds and 140 feet. Then I'll find the approximate distance over the next 5 seconds. And when we plug that into the equation that we went over in the definition, we get 165 feet. So we're going to continue to do this over the entirety of the graph that we have, with all of the trapezoids listed as T1, T2, T3, T4, T5, and T6. So when we add all of the areas of the trapezoid, we get a grand total of 1,175 feet. So this is known as the trapezoid rule, which is the area equals the limit as n approaches infinity, the summation n I equals 1 of f of x plus, or f of x sub I minus 1 plus f of x sub I over 2 times a x sub I. Again, thanks for watching.